Today, we want to finish up with the last few bits that we need to fill in integrating rational functions, which is just more algebra stuff. And I want to lead with this example. First thing that we notice is that the degree of the numerator is already less than the degree of the denominator, so I don't need to use long division. Next thing we notice, before we can even go to think about step 2, the zeros of our quadratic denominators, we look and we see we have a cubic denominator. So the degree of the denominator is 3. So we have more than a quadratic in the denominator, so we're going to have to use partial fraction decomposition, which means we're going to have to factor that denominator. So I want today, Wednesday, to be DVD bonus material day. Now, we know that since it's a cubic polynomial, we know it must have a real zero. We're not guaranteed a nice rational zero, much less like an integer zero. Although if it has an integer zero, we can see it's going to be, or if it has a rational zero, we can see what it's going to be, and it's going to be an integer. Well, we're not guaranteed that there's a rational zero to this polynomial. So this might prompt us to do the efficient thing and grab our calculator and draw a graph of the function to find out where it crosses the x-axis. But if we're going to grab technology to cope with this problem, why don't we just grab a computer and Wolfram Alpha and ask Wolfram Alpha what the integral of this function is? That would ruin all of the fun. It's like level 100 enchanting in Skyrim. You don't have to do anything anymore. So we could bring technology to bear on this problem to deal with what's the zero of this polynomial, or we could use some archaic knowledge, which is what I want to talk about today. Now, once again, this is just fun stuff. This is not something that's that I would classify as really useful. I would classify this more as neat. So we got to figure out if this has a rational zero. Because it's a cubic polynomial, we know it has a real zero, and we're hoping it has a rational one. So we know it has to have a real zero, so it's either a linear factor and a quadratic factor with complex zeros, or 3 linear factors. Has to be, because it has real coefficients. It is either a linear times a quadratic with complex zeros, or 3 linears. We know it has to have 3 complex zeros. They're either 3 real ones or 1 real one and 2 that are complex conjugates. Those are our choices. It's 3rd degree, so it has to have 3 complex zeros. Complex zeros always come in conjugate pairs from polynomials with real coefficients. So either 3 real zeros or 1 real zero and complex conjugates. A plus or minus BI is what I mean. So We know there is at least one real zero because it's an odd degree polynomial. So now what I want to do, since we're trying to avoid using any kind of technology and have some fun with this, that's right, I said fun, we're going to bring to bear some archaic knowledge. We're going to bring on the rational zero theorem, because we like old school stuff around here. So this is a theorem for polynomials. This is a theorem for polynomials. And what this says is that if a polynomial has a rational zero, then that rational zero will have a factor of the constant over a factor of the leading coefficient. So if a polynomial I'm going to write it down here and say P of x is a0 plus a1x plus a2x squared plus up to an x to the n. So a0 is the constant. And an is the leading coefficient. So if a polynomial P of x, here's a generic polynomial of nth degree, has a rational zero, then that rational zero will be a factor of the constant over a factor of the leading coefficient. So the numerator will be a factor of the constant, and the denominator will be a factor of the leading coefficient. That will be the form of the rational zero. So if we look at this polynomial, x cubed minus 9x squared plus 31x minus 39, 2 is not going to be a zero of this polynomial, because the only factors are going to be factors of 39 divided by factors of 1. So the fact that we've got 39 out here limits what we have to look at. So the possible the possible, oh wait, I think I have a backup. So for example, let's take a look at x cubed minus 9x squared plus 31x minus 39. If this polynomial has a rational zero, we'll have factors of 39 over factors of 1. That greatly limits things. So the leading coefficient is 1. And then the constant is 39. So if we look at the factors of the constant, we got 39 is 3 times 13. So 1, 3, 13, and 39. And then the factors of the leading coefficient, one. So our entire list of possible rational zeros for this polynomial are plus and minus 1 over 1, 3 over 1, 13 over 1, 39 over 1. If I had a leading coefficient of 2, I'd have 1 over 1 and 1 over 2, 3 over 1, 3 over 2, 13 over 1, 13 over 2, 39 over 1, 39 over 2. But leading coefficient was 1. We have these 8 possible rational zeros. Now we can just go through the list and find out which one works. Any questions? Now we just need to go through the list to find one that works. Any questions? So that means we have to do lots of different divisions. So we're going to have to do, since we're looking for a factor of the form x minus some constant, it's efficient to use synthetic division. Okay, since we're dividing by a factor, since we're looking for a form, since we're going to be dividing by x plus 1, x minus 1, x plus 3, x minus 3, since we're dividing by a polynomial of the form x minus a, we can use synthetic division. Since we're dividing by a factor of the form x minus a bunch of times, we can use synthetic division. Synthetic division is also a way to evaluate this polynomial at several different points. The other way we can think of this is that since we're substituting in a constant, substituting a constant into our polynomial, we can use synthetic division. Because the other way we can test these, each of these factors for a zero, to be a zero of this polynomial, is that we can just plug them in. But there's cubics, and there's like 3 cubed and 9 squared, and the 9x squared and so forth. So since we're going to be doing a repetitive process, we should look for a shortcut, and synthetic division is a cool shortcut that you may or may not know. Any questions?
So is there like a theorem that states to divide by x minus a?
No, we're just trying to figure out which of these numbers is a zero of the polynomial.
Oh, so that's okay. Got it.
So we're the possible zeros are plus and minus 1, plus and minus 3, plus and minus 13, and plus and minus 39. We've got 8 to check. Oh, this is of the polynomial x cubed minus 9x squared plus 31x minus 39. So we got to figure out if any of these 8 numbers are a 0 of the polynomial. We can do that either by plugging them in to see if they're equal to 0. Let's call this q of x. We can either evaluate q at all these points, or we can divide the polynomial by x minus the one that we're trying. So we either we'll either evaluate q of a for each of these values, each of these possible zeros to find the zeros, or we'll divide q of x by x minus a. To find the zeros. So the reason that I picked this is so I could talk about the rational zero theorem, and also so we could talk about synthetic division. So in synthetic division, we want to, so I'm going to first divide by x minus 1. So I want to do this division x minus 1 into x cubed minus 9x squared plus 31x minus 39. Now we're looking for a 0 remainder. That's how we'll find out if x minus 1 is a factor of this polynomial. So we start off with the same thing we did yesterday. X cubed divided by x is x squared. That's answering the question, how many times can I subtract x minus 1 from this polynomial, which starts with the x cubed? How many times can I subtract x from x cubed? I can do that x squared times before I get to 0. Then I multiply. X squared times x is x cubed minus x squared. And here we are subtracting x squared times x minus 1 from the polynomial. We're actually subtracting it from the entire polynomial, but it's only these first 2 terms that come into play. So the x cubes cancel out by design. If that doesn't happen, then something has gone wrong. -9 minus a -1 will give us a -8x squared. Now I'm asking the question, how many times can I subtract x from -8x squared? And that would be -8x times. -8x times x is -8x squared. -8 times -1 is positive 8x. And then I need to subtract. The -8x squared minus a -8x squared cancels out by design. If that didn't happen, then something's gone wrong. And 31 minus 8 is 20 something, 23. And then finally, we can subtract x from 23x 23 times. So let's subtract x minus 1 from 23x minus 39 23 times. And we find out that we got -39 minus a -23 is not 0. So 1 is not a 0 of this polynomial. We could also have found this out. We could have also found this out by trying to plug in 1. If we calculate q of 1, we have 1 cubed minus 9 times 1 plus 31 times 1 minus 39. So we get 1 minus 9 plus 31 minus 39, which is also the same, not 0. So another way to get through this division, which is also going to be a way to plug things into, you know what, we should actually figure out what this is. What's 39? I'm being lazy. What's 39 plus 20, negative 39 plus 23? 16? Negative 16. Is it negative 16? I'm not very good at arithmetic.
Yep.
Thank you. So one way we can do this is what's called synthetic division. And one of the messy bits about the long division process is keeping track of all these terms. Because unlike numbers, we can't just use place value to determine what the terms are. In numbers, we use place value, the tens place, the hundreds place, the thousands place, and so on. But in polynomials, we have to write x cubed, x squared, x, and then 1. We have to write what they are. It's like we have to write, when we write 23, we'd have to write 2 times 10 plus 3. And then we decided a long time ago, it's like, oh, why don't we just make sure that column, this one column is all the ones, then the next column is all the tens, and so on. Like I was there. So synthetic division looks at this and says, hey, we're just dividing by x minus 1, yeah? And long division is like, oh, yeah. And so why don't we just agree and try to use a place value business? And let's call this this polynomial just 1, negative 9, 31, and negative 39. And then let's divide this by, I know it looks all backwards, x minus 1. So I'm going to put a 1 up here. Now, the first thing that we did was we said oops, I didn't want to have that one be blue. Up here, we said we were going to do this 1x squared time. So if I make 1x squared, then what happened was I took the x squared and multiplied it. So what we're going to do is we're going to multiply the 1 times the 1, and that's going to be a 1. Because that's what happened over here. 1 times a 1 is it's going to be a 1x squared. And then we have negative 9 minus a negative 1 is a negative 8. So we could just add that here. Negative 9 plus 1 is a negative 8. Then the next thing that happened is this term. So what we're going after is this term right here. So we put a negative 8, we multiplied by negative 1, and we have the positive 8. So if we just take the 1 and multiply by negative 8, which is actually this negative 8 times this 1, this is the flaw in my education of synthetic division. I said do 1 times 8. Even though it's the same thing, better to say 8 times 1 goes here, but then it's not swoopy because we're going to multiply and then add. 1 times negative 8 is negative 8, and we set up the next subtraction that we do. 31 minus 8 is 23. And then 1 times 23 is 23. Negative 39 and 23 is negative 16. So synthetic division just says, hey, what if we use place values, even though this is a polynomial? Since we're dividing by an x minus 1, since we're dividing our cubic polynomial by a linear polynomial, let's just agree on the place values. And if we know, if we take a cubic divided by a linear, we'll end up with an x squared. So this is going to be an x squared minus 8x plus 23 minus 16 over x minus 1. Remainder of 16, the important thing was that this is not 0. Notice that the remainder is what we get if we plug 1 into the polynomial. So that's really cool. Now we've got a fast way of not only plugging in the values, it's pretty simple with 1, but we got a fast way of plugging in the values and determining if one of our 8 possible zeros is a 0 of the polynomial. So here we tested 1, now we'll just test -1 and go through all of them. If it seems like a lot of work, this doesn't even begin to look like a lot of work yet. That's kind of that's what I call the Einstein Maneuver. I don't know if you're familiar with the quotes, but Einstein once said, "Don't worry about your difficulties in mathematics. I assure you mine are greater still." He didn't say that because he was bad at math. He was an excellent mathematician, probably one of the greatest mathematicians of all time. He said that because he was explaining some math to people and said, "You think you got problems." And that's kind of just a jerk move, and we don't like to think of Einstein that way. We want to think of him being cool all the time. But he was human and therefore probably wasn't. So we're going to do our synthetic division. This works because we're going to divide. We're now dividing by x plus 1. So we're plugging in a -1. -1 times 1 is -1. Then we get -10. Then we get -1 times -10 is +10. And then that gives a 41. And then it's going to -1 times 41 is -41. And we add those together and we get not 0. We get -7010. So here we have x squared minus 10x plus 41 minus 80 over x plus 1. So -1 is not a 0 of this polynomial. So we go on to 3. So we're dividing by x minus 3. We're just going to agree that all the x's are going to cancel out, or all the highest powers of x's are going to cancel out in our subtraction algorithm. And 3 times 1 is 3. -9 and 3 is -6. 3 times -6 is -18. 31 minus 18 is some number, 13. 3 times 13 is 39. -39 and 39 is 0. So q of x divided by x minus 3 is equal to x squared minus 6x plus 13. We have found a rational 0. And moreover, we can see that that is the only real 0 we're going to get. So good, it was the 3rd one on the list, so lucky us. It's almost like I designed it to be the 3rd one on the list. Any questions? All right. So that was just so from the perspective of this particular problem, we have now rewritten we haven't even rewritten our integral. We can go back to our original integral. And we now know that the x cubed minus 9x squared plus 31x minus 39 is going to be x minus 3 times x squared minus 6x plus 13. And so we're ready to proceed with partial fraction decomposition. Like I said before, the reason that we're going through all this is because we don't want to just drop this into a machine and find out what the zeros are. Because if we're going to bring a machine to the problem, bring a machine to the whole problem. Any questions? All right. It's not always just about raw speed. I mean, people still run marathons. People still run marathons, but if it was just about getting from point A to point B quickly, then you would drive. 26 miles is a driving distance, and it would be a lot faster than walking. I mean, probably not in Southern California, but, and sometimes not in the Bay Area. But on Sunday mornings, when marathons are usually held, I mean, just drive. If the point is speed, just drive. Looking at you, Fremont. I haven't been to Fremont for quite a while, and it's the traffic that keeps me away. I'm just kidding. It's COVID. COVID is the answer to everything. Any questions? The other thing that I did not bring up, which is also a fun bit of information, is Descartes' Rule of Signs. Descartes' Rule of Signs tells you how many positive and negative real zeros a polynomial might have. And it's just based on the sign changes. So notice that the sign changes once, twice, 3 times. And this is why I did not use Descartes' Rule of Signs. Actually, that would have been useful because there were 3 of them. I only counted 2 previously. Oops. So notice that there are 3 changes in sign. And so that means there are 3 or 1 positive real zeros. So we could have brought Descartes' Rule of Signs to bear on this polynomial. I didn't want to go to a 3rd page. I'm going to a 3rd page. I must have had a different polynomial that I was thinking of. And then I just went with this, one of my standards. So the other interesting thing, which is fun with polynomials, is Descartes' Rule of Signs. And what Descartes discovered, actually what most certainly he did not discover, someone else did, and he just put his name on it, because that's how stuff goes. He said there are 1, 2, 3 changes in sign. So Q of X has 3 changes in sign. So Q of X has 3 or 1 positive real zeros. We found out that it was the case that it had 1, because once we found that first positive real zero at 3, we saw that after dividing, we saw that the other 2 were going to be complex zeros. So 3 or 1 positive real zeros. If we look at Q of negative X and count the sign changes there, so that's just going to change the odd powered signs. We see that we could have saved ourselves some efforts because there are 0 changes in sign. Q of negative X has 0 changes in sign. So Q of X has 0 negative real zeros. Going back to our previous problem, or the problem that we were working on, is, that was the previous problem. Going back to the previous problem, that means we didn't have to check -1 because we should have known that Q of X does not have any negative real zeros. So clearly today was brought to you by obscure mathematical facts that no one gets to learn anymore because we have computers and we think we have more important things to do. But here we are. Descartes' Rule of Signs, rational zero theorem, more about polynomials than you ever wanted to know. Any questions? Comments? Snide remarks? I was really thrown off today because I have my three black pens, which is the core pen. They all seem to be going out on me. So everything, like the rest, I got 2 more classes today. They're going to be primarily blue. So that messed with me a little bit more than it probably should have, but there it is. Like I said at the beginning of the class, who knows how the human mind works? It does weird things. That's why just restarting your computer and fixing it is the most human thing that computers can do. All right, that's it for fun with polynomials. If you're concerned about Descartes' rule of signs being used on a test, I assure you it will not be used on a test. Descartes' rule of signs, rational zero theorem, pretty much this integrating rational functions business, besides those 4 core integrals, are not things that I find appropriate for a test. Discussions, yeah, that's why we had that when we had the discussion and it said, hey, integrate one of these functions. That's fine. That's just a homework problem, and all bets are off in homework. But if there's going to be something that I call a quiz or a test, especially if there's going to be a time pressure, I am not going to give you trigonometric substitution or the other one. Yeah, phone call threw me off. So anyway, that's it for today. I will see you all on tomorrow, and we will start thinking about integration in terms of addition. Integration is just addition. That's it for today. See you tomorrow. Have a good day, and thanks for playing.